Hello, everyone. Now let's look at two rolling problems together. The first one is this. So we have a solid cylinder rolls down an inclined plane. We know the angle theta without slipping. So this is what we are given. So we know there is no slipping happening between the cylinder and the inclined surface from rest. The cylinder has a mass m and radius r. Then we have two questions to answer. First one, what is its acceleration? Second one, what condition must the coefficient of static friction mu sub s satisfy so that the cylinder do not slip? Okay, so we know when the coefficient of friction is big enough, then the cylinder will not slide down the plane here, but how big the mu sub s should be. So this is the second question. To solve this problem, step one, we got to have the right free body diagram. That is the key. So how do I draw the free body diagram? So let's look at, so we have a cylinder right here. We got to have a gravity. So mg is pointing downward. It is resting or it is against the plane. The plane will give it a normal force. What else? We know there is no relative motion between the cylinder and the surface at the contact here. And we know there will be a static friction force. The direction of the static friction force is always against the potential relative motion. So let's see, what if the cylinder slides? It will slide down. So therefore, the static friction force is pointing toward the opposite direction. It is pointing upward. And it is passing the contact point right here. So that's F sub S. Those are the three forces applied on the cylinder. So the cylinder will move and it will move down. The center of the mass will move down. At the same time, it will rotate as well about its own center. So there will be two kinds of motion happening. And this is what we call it rolling, because we not only see the translation, we see the rotation as well. Now, before we step on to write down the equation, let's decompose the gravity along the x and y. So look at what I chose here. I picked a oriented or inclined two-dimensional Cartesian coordinate system along the surface pointing down, that's x positive direction, and the normal to the plane, I have positive y direction. Okay, so now decompose mg into x. So construct right triangle. We have this force right here, and the magnitude is mg times sine theta. And along the y direction, so we have another component right here, and the magnitude is mg times cosine theta, and it is pointing along negative y direction. See, if I have two components here, I do not consider the mg anymore. So this mg and those two components, they're equivalent. We only look at one case. So I will not look at mg, I only look at those two components. Now let's write down or find out the total force along x and along y respectively. So along x direction, what I have here, I have this mg component, so mg sine theta minus Fs. Why? Because Fs is pointing along the negative x direction. So minus Fs equals what? So net force equals m times a. The a is the acceleration of the center of the cylinder. So when we observe the cylinder, the whole thing, the center, the whole thing is moving along the surface down. And the center will move, okay, along this line right here, along this linear direction. And I assume the acceleration is ACM. So then F equals MA. There's Newton's second law applied on the X direction. Then along Y direction, so the cylinder won't get into the plane, it will never leave the plane. So there will be no acceleration along Y direction, which gives us the net force equals 0. I have m minus mg cosine theta equals 0. So two equations. How many unknowns do we have here? We know m, we know g, we know theta, and we don't know what f is. So this is one unknown. ACM is unknown, and of course n, yeah, if so we can treat n as one unknown again, because this equation gives us some information about n. So two equations, three unknowns, problem not solvable. And we have to find some other relation there. And we do one more relation to solve for the three unknowns, even though, okay, we can solve for n from here, but this equation still has two unknowns, still not solvable. And don't forget this, because this static friction force is always less than or equal to the maximum static friction. And only for the maximum static friction, we have this relation here. Mu sub s times n equals Fs maximum. So that is only working for the maximum case. And we'll use that later. So now we'll focus on how can we get the A is the center of mass, the acceleration of the center of mass. So from here, okay, let's solve for ACM for now. So ACM can be expressed in terms of J theta and Fs divided by M. And the key thing is, how do I get Fs? Okay, so how do I know what Fs is? Now, let's consider the rotation of the cylinder about its own center of mass here. We know when Y is rolling here, the cylinder is rolling, it's rotating about its own center right here. And what causes the rotation? The torque. See, now when we look at free body diagram here, we know N and those two mg, they all pass the center of the mass. So none of them generate a torque. And torque is the reason to make it rotate. But Fs, there is a force and there is an arm from the center to the force here. So this Fs, the friction force, will generate a torque around the center. So this torque causes rotation. So from the rotation right here to step one, we calculate the torque. Torque equals force times the arm. Force, Fs, arm is the arm. Along counterclockwise, so we let it be positive. So now we have torque equals Fs times R. And torque equals what? I times alpha. Newton's second law on rotation. The net torque equals the moment of inertia times the angular acceleration. Alpha is the angular acceleration. So now we can find the expression of Fs that equals I moment of inertia times alpha over R here. And then, so if we plug this into the expression here, we know we still have A here and we have alpha. Can we relate those two? That's the key to solve this problem. Since there is no slipping here, and we know there is a relation between the linear acceleration and the angular acceleration, ACM and alpha, they're related by the radius of the cylinder R here. So ACM equals R alpha here. So what I can do now, I can solve for alpha in terms of A and then plug it in the expression of S. Now I have Fs equals I times A center of mass over R squared. Now we plug Fs back to equation 3 here. And the left side, we have ACM and then equal J sin theta minus, this is Fs. I see this, what I got here, IA over R squared and times ACM. That's the Fs. Don't forget we have the divide by M here. So then we have one equation. In this equation, there is just one unknown, ACM and ACM. So this single unknown appears at the two locations, appears on both sides of the equation. And then we just treat it as a simple linear equation and move this term to the left side, combine like terms, and then divide the coefficient. We got the acceleration of the center of the mass, ACM, equals this one, J sin theta over 1 plus I over mr squared. And then if we multiply m on every term here, we can get another expression, mj sin theta over m plus ICM over r squared. This expression works for what? Any circular body it does not need to be a solid cylinder. It could be a pipe. It could be another shape of the disc. So as long as it had a round surface and it rolling down, and it will have its own eye about its own center of mass here. And then we will always have this, the ACM here. So different from what we have here, we can get what? We can get the center of mass determined by the mass, the radius, and the eye here. And center of mass, the linear acceleration, we solved equation 1. And go back to this specific problem because we are given now we have a solid cylinder and we know ICM, the center of mass, the moment of inertia of about its own center of mass for a solid cylinder equals 1/2 mr squared, and plug it in here. We know we can simplify this and eventually we can have a simplified expression for the linear acceleration of the center of mass. AM equals, ACM, center of mass equals 2/3 g times sine theta. If we have another body, if we have like a pipe or we call it a loop, then ICM will be mr squared. This expression will turn into another one. But this is for a general case. For any round body, which is rolling down without slipping, the center of mass always have a linear acceleration in this expression here. This is the question A. Now let's go back here. We want to know, so what is the condition must satisfied by the mu sub s so that cylinder does not slip? So in another word here, we want to know what is the minimum, the smallest coefficient of static friction should be there, then there will be no slipping happen. Okay, so now let's move on to the question B. And again, so for the Fs, because here, so we have found Fs in terms of IA and R squared, because I know ACM, we got ACM already, plug ACM to this expression here, we can find the friction force Fs equals this one. Again, everything is pure mathematics, so we just simplify the expression. Then we got the friction force is equal to this one. Now we go back to the problem. Since there is no slipping, that means our actual static friction force is less than or equal to the maximum static friction force, which is equal to mu sub s times n. So because this is the actual static friction force, this is the maximum. So the actual is always less than or equal to the maximum. And we plug the expression of Fs into this inequality right here. And don't forget n equals mg cosine theta. So now we cancel mg here, and then we can find the expression of the mu sub s. So mu sub s is, so we flip the two sides of the inequality. We got mu sub s is greater than or equal to one expression like this, so divided by cosine theta divided by mg, we get expression here. And again, this works for any round object when they have the radius of r. And for the solid cylinder here, we have the ICM, the moment of inertia about its own center of mass, equals to 1/2 mr squared. So this expression can be simplified as 1/3 of tangent theta. Okay, so this mu sub s is only for the solid cylinder. And again, if we have another body, that will be another expression, but they all come from here. They share the same expression as for the general case. Okay, so this is the first type of slipping, rolling without slipping here. There is another very similar one. Second problem, what we see here. So we kind of see the similar problem. Okay, see, zoom here. Still, we have a solid cylinder rolls down. And along this inclined plane right here, we know the mass with the radius here, and plus we also know the mu sub k. So it has m and radius r here. We also know the kinetic friction coefficient is mu sub k here. So this is the wheel or the cylinder rolls and slips. So it is slipping along the plane here. And now we need to answer the two questions. Number one, we still want to find out what is the linear acceleration of the center of the mass. Second one, we want to know what is the angular acceleration of this cylinder around its own center of mass. So still two questions here. And we are going to draw the free body diagram again. So for the body right here, we still have the gravity. We still have normal force. And now we have the friction force because it is slipping. Therefore, there is relative motion between the cylinder and surface right here. So the point on the cylinder is not resting on the surface. It is sliding. There is relative motion. We'll have the kinetic friction force, Fk. So Fk is pointing toward the negative or opposite direction. We have Fk right here. Still, we follow the same idea. We set up the coordinate system. X goes down along the surface, Y is perpendicular to the surface. So after we have the free body diagram, we do the same thing, decompose mg into the X component and the Y component. This is mg sine theta. This is mg cosine theta. Then get net force along X direction. X direction, we have mg sine theta. Then we have Fk, so minus Fk, that's net force, equals what? Equals ma cm. Note in the second law, along the X direction. What else? Along the Y direction, still, the cylinder won't leave the surface. When you get into the surface, it just stay on it. So the net force along Y direction is always zero. I got m minus mg cosine theta equals 0. And don't forget, so again, we count. Fk is unknown, ACM is unknown, N is known, 2 equations, 3 unknowns, and we need one more piece of information to solve the problem. What is that? N and Fk are related by what? By mu k. So Fk is always equal to mu sub k times N. Combining the 3 equations right here, so I call it equation number 3. And so first we solve for Fk equals mu k times mg cosine theta, then plug it into equation 1. Then what we get mg sine theta minus mu k mg cosine theta equals ma. And then combine like terms on the left side, then divided by m, we got the expression of the acceleration of the center of the mass, ACM equals this one. And we can factor g out, get g times parentheses, sine theta minus mu k cosine theta. So for this one, I want to pay attention to this. See, the linear acceleration of the center of mass only depends on what? The angle of the inclined surface theta and mu sub k. G is a constant. It has nothing to do with how big the cylinder is, the R, or what the mass is, or what is its center of mass. It has nothing to do with its dimension, the material, or the mass. Okay, for all around the body, when they are slipping and rolling with slipping down the inclined surface here, the center of mass has the magnitude of this one. It depends on the theta and mu sub k only. Right, so that means what? For a solid cylinder or for a steel one or aluminum one, different materials, or there is a the different shape, like if it's a loop, not a solid cylinder here, as long as mu sub k is the same, they all have the same linear acceleration. So this ACM. All right, so this question 1. Question 2, we want to find out, we know And there is torque generated around its own center here because the Fk had torque here. It's going to rotate. We want to know what is the magnitude of this angular acceleration. And how do we do that? Again, apply Newton's second law on the rotation. What causes rotation? The torque. And then calculate the torque around the center of mass. See, mg, no torque. And there is no torque. Only Fk has the torque. And so the torque equals what? Fk times r. Counterclockwise, we let it be positive. So we do not need to write down the positive sign here. We know it's going to rotate counterclockwise. Equals tau equals what? I times alpha. This is Newton's second law applied on a rotation. Then what we have here, we have, okay, so plug Fk equals mu k n equals mg cosine theta, and we can solve for the up. The angular acceleration equals mu k mg cosine theta times r over ICM. So now we'll see the angular acceleration not only depends on the mu sub k right here, it depends on what? It depends on the radius of the cylinder, different size of the cylinder, they will rotate in different angular acceleration. And also, okay, depends on the I, and I depends on M and R. Okay, so for a solid cylinder, we have a simple expression of the I, the moment of inertia equals 1/2 mr squared, and plug this into the expression of the angular acceleration. We can have a simplified expression for the angular acceleration for a solid cylinder when it rolls down and slipping on the inclined surface. The angular acceleration equals 2 mu kg cosine theta over r. And for like a loop, then we'll have another expression because that I will be mr squared. When we put that in, we'll have a different expression. Okay, so make sure you know how to work on those two problems, please.